আমাদের সাউন্ড অফ আছে।
আপনার স্যার সাউন্ডটা অফ করবেন, এখন অফ করে রাখবেন, পরে আপনি যখন শুরু করবেন তখনই করবেন। Okay, good morning everybody. Today we are going to start our DBT sponsored 2-day national conference on research development of chemical research being implemented in biology and medicine, organized by Department of Chemistry, Mugberia, Gangadhar, Mahavidyalaya. It is my great opportunity to inform all of you that to popularize biotechnology activities in India, Department of Biotechnology, Government of India has approved this conference and provided financial assistance to us under conference travel exhibition and popular lecture scheme. So at the very onset, I wish to convey my gratitude to DBT CTEP Management Cell, Government of India, for generating financial support for this 2-day national conference on a virtual platform. As you know, the goal of fundamental science at the interface of chemical sciences and biology is to understand the life in chemical terms. Our ability to accomplish the translation of biology into chemical terms is closely related to our fundamental understanding of life's machinery. However, for most people, the real impact comes when we can use that understanding to improve our lives. Along with the quest of fundamental aspects, scientists have always been interested in designing practical applications of scientific advances in the form of devices, drugs, catalysts, etc. for mankind. After the emerging discovery of a metal-based drug, cisplatin, all of you know, which enlightened the world as a promising anti-cancer drug, several research findings culminated the ideas of inclusion of metals in medicine, and in respect to this, a greater interest had also been observed in the last decades for designing new compounds and devices towards their applications in biotechnology and medicine. Besides, more and more researches in the chemical sciences are going on, particularly for the prevention, diagnosis, and treatment of diseases. The students belonging to this rural and backward area of West Bengal are completely unaware about these advances in chemical research. So the main objective of this conference is to provide awareness, information, and knowledge to the target audience, mainly students and faculty from host and nearby colleges, regarding the development of chemical researches towards their contributions in biology and medicine for the benefit of society and human welfare. It is no doubt to say that this conference is very much relevant to the thrust areas of biotechnology and its development. So I think the interactions and deliberations that will be happened in this virtual platform will be much more helpful and enthusiastic to the researchers, faculties, and students of chemistry, biochemistry, biotechnology, and biological sciences streams. Today, in the inaugural session, we have with us the gracious presence of several dignitaries. Professor Dr. Swapan Kumar Mishra, Principal Mugberia Gangadhar Mahavidyalaya and President of the Organizing Committee. Professor Dr. Ashutosh Ghosh, Vice Chancellor, Rani Rasmani Green University and Professor of Department of Chemistry, University of Calcutta, as Honorable Inaugurator of this conference. Professor Dr. Amit Bosak, INSA Senior Scientist, IJAR Kolkata, and former Professor, Department of Chemistry, Indian Institute of Technology, Kharagpur. And Professor Dr. Praloy Maiti, School of Material Science and Technology, Indian Institute of Technology, DHU, Varanasi. Professor Dr. Tanmoy Pathak, Department of Chemistry, Indian Institute of Technology, Kharagpur, as distinguished speakers of this two-day conference. Besides distinguished faculty members of our college and also from other colleges and universities, distinguished delegates, my dear students and ladies and gentlemen, I cordially thank to all of you for joining the conference through this virtual platform today. Now, I would like to invite our principal, sir, Dr. Sapan Kumar Mishra, to deliver his welcome address in front of our participants. Sir, please.
Thank you, Bidanu. Good morning, everyone. We are grateful that we have at present 4 eminent personalities in this webinar. Respected inaugurator, Professor Ashutosh Ghosh, Vice Chancellor, Rani Rasmani Green University. Respected speaker, Dr. Amit Bosak, School of Bioscience, IIT, Kharagpur. Dr. Praloy Maiti, Professor and Coordinator of School of Material Science and Technology, IIT, DHU. Respected Dr. Tanmoy Pathak, Professor, Department of Chemistry, IIT, Kharagpur. Our beloved Dr. Bidhan Chandra Samanto, convener and speaker of this program, and HOD of the chemistry of the college, and coordinator Star College scheme. My dear colleagues, researchers, students, and audience. Now it is my great opportunity to welcome all of you in this webinar on recent development of chemical research being implemented in biology and medicine. Actually, medicine advances from Ayurveda to use of the convenient ways of allopathic drugs to targeted use of therapeutic drugs. A small example I would like to share here from my personal experience about asthma that I have been suffering for years. Earlier, I had to take edible drugs. Actually, edible drugs I most rely on inhalant at present. The inhalants act directly on lungs and alveoli rather than the common routes from small intestine to villi to the blood and then to lungs alveoli. This process minimizes the chance of side effect caused by the drug in our body. Like this, there are different therapeutic drugs that are being used directly for targeted afflicted cells or parts of body. Actually, nanomaterials, which are very teeny particles, are used as new type of medicine. For instance, nanogels are widely used for transdermal drug for recovering muscle pains or injured area of our body instead of taking painkiller tablet. Ocular drugs for eye infections in means of topical eye drop are another example in this category. Similarly, topical chemotherapy, especially for the skin cancer, is quite popular nowadays. As science advances, different new chemicals compound and new techniques are discovered. that is currently the world is suffering from the pandemic, from the COVID-19, and we have enormous faith and hope to the scientists community to discover new type of topical therapeutic drugs and medicines to fight against this virus as well. We are very much grateful to the Department of Biotechnology, Government of India, for providing financial support to the Department of Chemistry of our college for organizing 2 days virtual national conference on recent development of chemical research being implemented in biology and medicine. I do hope that this sort of interactions and exchange of news and views in this webinar will greatly enrich our researcher, students, as well as it is helpful to equip the people with proper implementations. It is my great pleasure that the Department of Chemistry of our college has been taking initiation to organize this type of conference with financial support of DBT. Last but not the least, I express my profound respect and best wishes to all respected guests and speakers for taking interest in this matter and giving us their valuable time. Thank you. Thanks, all of you.
Thank you, sir, for your valuable talk and welcome address. Thank you again, sir. Now, it is the time to officially inaugurate this DBT sponsored 2-day virtual national conference. May I now opportunity to invite Professor Dr. Ashutosh Ghosh, Vice Chancellor, Rani Rasmani Green University, to inaugurate the conference officially by his valuable inaugural speech. Sir, please.
Thank you, Dr. Samanto. I am audible?
Yes, sir. Yes, sir.
Okay. Good morning, everybody. It is my honor to inaugurate the conference, Recent Development of Chemical Research Being Implemented in Biology and Medicine, organized by Mugberia, Gangadhar, Mahavidyalaya. I would thank Dr. Bidhan Chandra Samanto, Head, Department of Chemistry, and the convener of the conference, Dr. Swapun Kumar Mishra, Principal of the college, for inviting me in this session. First of all, I must say that although I do teach and research in chemistry, I do not have much idea about the application of chemistry in biology and medicine. It's not my area of research or teaching. It's true, so I confess this one. I think Professor Boshak, Professor Pathak, and Professor Maiti, they are here. They have a lot of experience in this field. And you will learn, all the participants, I think all of you will learn a lot of things in this area from them today and tomorrow. In spite of that, I am not an expert in this field till I accepted the offer to inaugurate this conference when I get the invitation from Bidhan, because you know that I have a kind of association with this college. Few years back, I went to this college for a lecture, and I delivered lecture. I was really very impressed, impressed with the attitude of the teacher, I would say, because this college is situated in a very remote area. All of you know, the students, you know, the participants, you know that this college is situated in a remote area. But what I have seen, the teachers, they are doing their best. They are trying their best to provide the best education what they can do for their student. I have seen the laboratories. Laboratories they are good. They have a very good campus. They have and all especially the attitude of the teachers. We need this kind of teachers. We need this kind of attitude. We need to educate our students so that they are they are the undergraduate students. So they should have some kind of exposure, beyond their syllabus. And the teachers used to provide those kind of exposure. But most importantly, which I was really very impressed, that the teachers of the colleges, which usually we don't find in the West Bengal, in most of the West Bengal colleges, we don't find, the teachers are writing projects for the funds, and they are getting funds for doing research. This is I think it's a very good attitude from the teachers from all subjects, especially in the science. I have seen in the southern part of India, the many teachers, the number of projects that they are submitting us much more than the college teachers submitting from the West Bengal. So we need many college teachers to submit projects to different agencies. I also tried to arrange a lecture with Bidhan, the academics lecture workshop with Bidhan in this college, but unfortunately, due to the paucity of fund, we couldn't arrange this. We tried our best, we tried many times, but we failed. Anyway, but I'm really happy that the Bidhan could manage the fund for this conference. And I told Bidhan that I am not exactly the expert in the biology and medicine, so it won't be it won't be prudent to give a lecture on subject, because I am really not an expert. Professor Bosak and Professor Pathak, Professor Maiti, they are expert in this field, so it is better that they give the lecture, the student learn from them, not from me, because I don't know much in this field. So that is why really I feel today very good that Professor Bosak and Professor Pathak is there, Professor Maiti is there. It's really the students, the participants will be enriched. But just I won't talk much, but I will share one of my experience which is relevant to this field. Just I am. Hello.
সত্যজিৎ তুমি মিউট করো, সত্যজিৎ মাইতি মিউট করো। Yes.
Just I was born and brought up in a village, in a remote village of Hooghly district. So before I was born, my father, he was a farmer. So in mid 50s, he was diagnosed tuberculosis. So he was in his late 30s, but diagnosed tuberculosis. So that time, some of my relatives, they are also suffered from tuberculosis. My neighbors also suffered from tuberculosis, and all of them did not survive. All of them died whenever there was tuberculosis. So people were taking it granted that there is no chance of survival. In fact, you will see the many. I have seen the daughter of Rabindranath Tagore died of tuberculosis. The elder sister and mother of Marie Curie died of tuberculosis. Uru Datta died of tuberculosis. You will see many people that time, so before 1940s, before 1950s, many eminent people died of tuberculosis. So tuberculosis was such a disease that whenever where that you are suffering from the tuberculosis, so people are thinking that he will die. So my mother, as a last attempt, my mother tried. My mother called a doctor. He was an MBBS doctor. It is the mid 50s. So think the timing. It is the mid 50s. So my father was suffering from tuberculosis, and everybody lost hope. So, but my mother didn't. You can say didn't. Thought that maybe just she wanted to try. So she called a doctor, and that doctor was MBBS doctor. And in the villages that time, to get a MBBS doctor is it's very rare. You won't get an MBBS doctor in a remote village. So he was far, and still I remember my mother told me when I was young, when I was a children, that he took a visit of ₹4. That time it was much, that ₹4 visit for an MBBS doctor. So the doctor came and he examined, and he told that yes, it is tuberculosis. He's suffering from tuberculosis, and he wrote the prescription, he wrote some medicine. And while he was leaving, my mother, naturally, my mother asked the doctor while crying, she was crying and asked the doctor, বাঁচবে তো আপনার কি মনে হয়? The doctor, he was very confident. The doctor told that হ্যাঁ এখন আর ভয়ের কিছু নেই, এর ওষুধ বেরিয়ে গেছে, এই টিবি অসুখের ওষুধ বেরিয়ে গেছে, আপনার ভয় নেই, ওষুধগুলো আমি যা লিখিয়ে দিলাম এগুলো খেয়ে নিন, দেখবেন ঠিক হয়ে যাবে। শুধু এই কথা বলে চলে গেলেন। কিন্তু এই যে কথা, that's this, you know, only this conversation my mother still remember when she told all of us about this conversation. She told that it is just it is just like a god, the doctor is just like a god, because my mother bought all this medicine, and my father survived. So it was a miracle that time. So that is why as it was a miracle that time, my mother and my father and my relatives, they are thinking that this doctor is God. But as we know, that doctor is not God, that this doctor is not God. The God is the medicine. The medicine, the TB, for the TB, the 1945 or 46, in the mid 40s, I will say that this medicine like streptomycin, the first medicine we got, and then also we got some other medicine. We also get the para-aminosalicylic acid, and also isoniazid. And the combination of this medicine, so in mid 50s, all these medicines are available, and you won't see many people died of tuberculosis after the mid 50s or 60s. You won't find many people died of tuberculosis. But before that, you will see a lot of change in this period. So why do we see these changes? Because of this medicine. And who discovered this medicine? Most cases, the chemists, they discovered the medicine, and then the biologists, they check, their activity for the different diseases, and whenever they have found that the anti-tuberculosis activity of this medicine, all these medicine are found. In my childhood also, in my early days, we have seen so many people suffered from leprosy, or suffering from leprosy, and we saw many people with deformed leg and hand, the finger. But nowadays you won't see any such people. Because why? Because we have good medicine, good chemicals for this leprosy, and this multi-drug therapy is really any kind of leprosy people can be cured with this kind of medicine. And the people, now people know that this is not a curse, this leprosy. This is just another disease, and it is curable. And it is curable by chemicals, it is curable by doctor, it is not necessary to the touch of the god to cure this kind of leprosy, disease like leprosy. But for many other diseases also, you think about the cholera, you think about the smallpox, you think about the typhoid, many such diseases, before 1930s, before 1920s, many people used to die with when they suffered from this kind of diseases. You will see many people, old people, we have seen many people, all of them were talking about these diseases, this cholera, this smallpox. Now, as you know, now I think young generation, the students of this, the participant of this conference, the young participant of this conference, you have never seen a patient who has suffered from the smallpox. Probably, and cholera is also, suffering from cholera is also very, very rare. And no one is thinking that as he is having typhoid, then he will die. So we are not thinking of that, because we have a lot of medicine. But we didn't, as you know, we didn't win all the diseases, because in the last year, this from the 1919 or in beginning of the 20s, the 2020s, what we have seen, that COVID-19. when the COVID-19 started, we understand our limitations. We understand that we have, there are a lot of diseases and lot of diseases which will come. We don't have medicine for that. We don't know what to do with the diseases, how to cure those diseases, how to treat those diseases. So that is why we have to continue our research. We have to continue our research. We have to continue to synthesize some new chemicals which will cure the new diseases. So this kind of research, search for new chemicals should continue and will continue. And this is the future of our research. And I think we not only the research is important, the awareness is also important, for the diseases, for any kind of diseases, especially if the disease is new, we need some kind of awareness, and for this kind of awareness, I think that always this kind of conference is necessary, where the people will be educated, people will learn. We can learn many things from there, but these are not the alternative of the conference. So I believe, so this kind of conference, it will help the people, it will instill interest in the participant to learn about the diseases, to learn about the different chemicals which are useful to cure many diseases, and our experts are there. So I will request all the participants, please listen all the lectures very, very carefully, and ask question. If you want to know anything, please ask question to the experts. You will not get chances, so often. So please take advantage of this situation, I would say, and please listen to the lecture. Just I would request you again. So I thank you all for to be present here, and also for your present here. Thank you very much.
Thank you, sir, for your very much lucid and nice inaugural talk. We are very much appreciating to your experience that you have shared in front of our participants and in front of us. Thank you, sir, for sparing your valuable time for us. Now, before going to start our technical session 1, the e-copy of the book of abstract of this conference will be published, and I may request to Professor Dr. Ashutosh Ghosh sir to publish this e-copy officially by sharing his screen. Sir, please.
Which one should I share?
Sir, e-copy of the book, a PDF file.
PDF file. Wait a minute. Where shall I get it? I don't get it. It is with me in my mail. Where it is?
Yes, it is in your mail.
Okay. Wait a minute, please. Okay.
Thank you.
Join the e-copy book abstract. Yes, we got it. Wait a minute, please. Takes a bit time because it's slow. And say how to share screen.
Share screen option.
Yes, and then share.
Click share.
Okay. Wait a minute.
Okay, this is coming.
It should come. But it is taking a bit time because my computer is slow.
Okay, no problem, sir.
So this is the technical problem. This is, I think this is a wrong one. Wait a minute. Wait a minute. It should be somewhere. It is the ebook. So this is the ebook. It should come now. Wait, please. It's okay?
No, sir.
Vidhan?
Actually, again,
Could you
share
see?
your, again, share your screen. Again, share your screen, sir.
Okay. Now I'll share again. Share and share and say, but where it is? Why can't I see it? But I could see it earlier, but I don't see it. Why? There is some problem, I think.
Actually, sir, open the file first. Open the file first.
Okay. Wait a minute, please. There's some problem with my computer, probably. Vidhan?
Sir.
There is. It seems that there is some problem with no.
No, it's coming, sir. It's coming, sir. Yes.
Yes. So this is the yes from the desk of the coordinator, and then this is the invited lecture. That is the antibiotic resistance and the battle to overcome, Professor Bosak, and then. Then lecture 2 is a sugar modified inhibitor of ribanolase. Professor Pathak will talk about that. And then materials and healthcare. Dr. Maiti will talk about that. And then again, it is Vidhan will talk about this one. And then there will be oral presentation of some student. Okay?
Okay, sir. Thanks.
Okay.
স্যার ধন্যবাদ স্যার আপনাকে।
Thank you.
হ্যাঁ স্যার।
Thank you, sir.
Thank you.
Sir.
So please continue with your program.
Okay, sir. Thank you.
Okay.
Sharing the sir stop করুন। হ্যাঁ।
করে দিচ্ছি দাঁড়াও। Wait a minute. I should stop sharing. It's okay?
Okay, sir. Thank you. Okay, sir.
Please continue.
Okay, thank you again, sir, for your kind assistance. Thank you. Now, technical session 1 will be started. In this session, there is one distinguished lecture from Professor Dr. Amit Kumar Bosak, INSA Senior Scientist, IJAR Kolkata, and former Professor Department of Chemistry, IIT Kharagpur. The session will be chaired by Professor Dr. Praloy Maiti, School of Material Science and Technology, Indian Institute of Technology, BHU, Varanasi. I request Professor Maiti sir to chair this session and conduct this session. Sir, please, over to you.
Thank you, Dr. Samanta, for your invitations to attend this meeting that I think you have organized so nicely, being in a remote college, and Professor Asuda has explained everything about your college and other things. So I think it is my proud privilege to introduce my teacher, Professor Amit Bosak, who is an outstanding scientist in organic chemistry. And Professor Bosak obtained his PhD from chemistry from Calcutta University. And then subsequently he did his DPhil from University of Oxford. And then he was a postdoctoral fellow at Johns Hopkins University before joining IIT Kharagpur in 1991. That time I was a master student in that same department. So that's the proud privilege of us being a student of Professor Bosak. And he served Presidency College And the important areas of his research is the development of the artificial DNA and protein cleaving agent. And on the other hand, the cyclizations and the development of protein and small molecule capture agent are the other active research area. And Professor Bosak has visited the chemistry research laboratory of Oxford University between 2011 and 12. And he is the fellow of all major Indian academies, and which includes INSA and the National Academy of Science, and then including West Bengal Academy of Science and Technology. And he is also the recipient of J.C. Bose National Fellowship and CRSI Silver and Bronze Medal. And he is Pfizer Endowment Lecture Award for his research accomplishment. He is, in one word or in brief, is an outstanding scientist in the chemical science area. And he is one of the respected scientists in India. So, sir, I would request you to give your talk.
So should yeah, am I audible to everybody?
Yes, sir. Yes, sir. Yes,
Okay.
sir.
Yeah. First of all, let me start by saying thanks to Professor Proloy Maiti, Proloy, yeah, for your generous introduction, which makes me a little nervous because outstanding word is reserved for really outstanding people, not for me. Okay. But anyway, all the best to you. You are now IIT BHU, which is where you are a stalwart now. Everybody is treating you as a stalwart. And regarding today's conference, first I express my thanks to Bidhan for pursuing on me to give a lecture. I actually completely forgot that when I said yes. But anyway, when he said that this has been approved by DBT, so I was in a fix because there are other people who are more learned, like Professor Pathak is there, and then Proloy himself is there. All these people are there. But anyway, I think it's a great thing to organize this type of conference or seminar or webinar now in a college where the students get a very rare opportunity to listen to the modern developments or the direction where chemistry is now heading. That is, I think, a very important aspect. Then I should express my sincere gratitude to the principal, Dr. Professor Shapon Kumar Mishra, for his, I think, overall guidance given to the college, whatever the college is doing, especially organizing this type of symposium. I think without the head or without a principal who is very encouraging, these things don't happen. Okay, I think his encouragement must have helped Bidhan to organize this type of conference. Then I listened to what Sir Ghosh, Ashutosh Ghosh told. I think I was really impressed about this discovery of streptomycin, and this is what is called luck. Now, in the 1950s, this streptomycin was discovered. So people getting tuberculosis before 50s, they all died. But after 50s, this medicine was made available. So I think thanks for bringing all these issues. I think what our students need to know is not only the chemistry that is going on now, but we should also look backwards and see how the things have been have come out and developed. Okay, I think with these few words, let me now start the lecture. And I request Proloy to interrupt me because I have a tendency to cross the time. Please interrupt me and say about the time that when what is allotted to me. If I cross that limit, please let me know. Okay, now share screen. Just a second. Share. Is it visible to everyone? Let me see. Only this.
Yes, eligible.
Yeah, only this thing is there. How to remove this?
This thing, actually, sir,
Hide. How to hide this? I was just thinking.
view option exits full screen. Is it okay, sir?
For me, it is okay. No problem. But you are
Okay.
whether it is.
Yes, sir. It is now okay.
Sir, it is okay, sir. It is fine.
It is okay. Okay.
Okay.
And this one also I shift. Okay. So basically, the lecture topic is the never-ending battle against microbial. The never-ending battle against microbial infections. Okay. Basically, Professor Ghosh was telling, Ashutosh Ghosh was telling about this tuberculosis problem. He was talking about an infection by a particular microorganism. And if you look a little bit philosophically, that every living being has the right to live. A right to live, and at the end of the day, every living being will die. That we know. But every living being has the right to live. So whenever you start killing something, so that whatever, if it is a microorganism, if it is an animal, if it is another human race, all these things, so they will always try to protect themselves and will try to develop new weapons to resist the weapon that has been used to kill them. Okay, so that's why whatever we have done so far, we have discovered so many medicines, so many antibiotics, antibacterial agents, everything is there. But when we are targeting living things, always remember that living things also will hit back at some point of time. And the existing set of medicines will slowly become ineffective. That's why the title says that the never-ending battle against microbial infections. Okay, so let me, Bidhan, is the audience mostly students? Is it so that?
Yes. Only student and few faculties are there.
Okay, so I will try to make it as simple as possible.
Yes, sir. Researcher are there. Research scholar are
Yeah.
there.
Oh yeah, some research will be there, but basically I will try to make it simple in simple terms. Okay.
Okay.
Can you see the entire screen? Are you seeing the entire screen?
Yes, sir. না ছোট নিচটা একটু কেটে যাচ্ছে মনে হচ্ছে।
হ্যাঁ, এইটা কি করে এটা দেখো তো এবারে আবার এটা এদিকে চলে এলো, এই তো মুশকিল দেখি। আচ্ছা, এটাকে মাইনাস করলে বোধহয় হয়ে যাবে। হ্যাঁ, এই তো ঠিক আছে, এবার দেখো তো।
হ্যাঁ স্যার,
ঠিক আছে।
হ্যাঁ স্যার।
So let me start by saying that what is an infection. That we always tell that I am suffering from influenza or typhoid, all these things. So infection, so we'll start from the very basics. An infection occurs when a microorganism enters our body and causes harm, right? There are two kinds of microorganisms. One is called pathogenic ones, which causes a disease in the body. And some microorganisms, they don't cause any disease. And on the contrary, sometimes they help us. And there are many organisms which help us, like some organisms which are present in our gut, in our intestine. They actually make chemicals like vitamins, which are very essential for our well-being, for our digestion especially. Okay, for our immunity. Infection basically is caused by a microorganism, which is a pathogenic microorganism. Now, what microorganism is a general term. It includes bacteria, it includes virus, it includes fungi, It can include parasites, all these things. Okay. Now, amongst all these, virus is little bit of a is more challenging than the other ones. This is because the virus always need a host for their amplification, for their survival. On the other hand, the other one, the bacteria or fungi or the fungus, they can actually grow by themselves. Okay, and occasionally they enter in the body and then start growing and ultimately start the disease. But virus, the problem is once, because they don't have any way to live by themselves, so they need a host. So when they come inside the body, they quickly enter into our cell and then use the same machinery for their amplification. So anyway, we are now talking about, mostly we'll be talking about the bacteria, antibacterial agents, the antibiotics. Okay, just to let you know that because of the last 2 years, we have this problem of virus, this pandemic by the COVID-19. So all attention are now being given towards the COVID-19 infection and how to develop vaccines, how to develop drugs. So most of the research is now concentrating there. But what happened in the last 20 years, which is now has taken a backseat, that is the infection caused by bacteria. Because many of these drugs, like streptomycin, what Professor Ashutosh Ghosh was telling, as soon as he told, I actually thought that it is good to know who discovered this streptomycin, which has saved his father's life. It was by Waxman in a university called Rutgers University, quite famous university. At Rutgers University, he discovered many antibiotics. One of them is streptomycin, and you see the structure. Okay, Professor Pathak will be happy to see this structure because of its presence of this sugar in this molecule. Okay, and he deals with sugar molecules. Okay, so anyway, it's a natural product. It's an antibiotic. So basically, what I am saying that although we had many antibiotics in our arsenal, but today we are in the risk of losing these antibiotics. Losing these antibiotics means these antibiotics are losing their potency. So the drugs which were treatable earlier by penicillin, by streptomycin, etc., today the microorganisms have developed their resist. Yes, can anybody? I think someone's mic is not mute.
Okay. Muted. Continue, sir. Continue.
So basically, those drugs are slowly losing potency, and that's a great danger looming large in the world. But as I said, because of the pandemic, most of our attention is now towards treating the COVID-19. But I think this will again come back once the COVID-19 pandemic slows down. Okay, it is already slowing down, but I think it will go once, because that is a natural phenomenon. It happens earlier. It happened in 1920, the Spanish flu, 1918 to 1920. So now this is the other flu. In between, there were other viral infections that has come and go. So it will definitely go at some point of time. Okay, now let us see about the antibiotics. Okay, the key facts today that antibiotic resistance is one of the biggest threats. I told you it's the biggest threat because it kills more people than what the virus may be killing at the particular point of time. But overall, in a 10-year span, antibiotic resistance resistant bacteria are killing more people today than previously. Antibiotic resistance can affect anyone of any age in any country. Antibiotics, actually, age is not is an issue. Okay, like virus, we say that the older people are dying because of comorbidity. Antibiotic resistance means the antibiotics are not working inside the body. That can happen to anyone, irrespective of age or race of the country. Okay. Antibiotic resistance, how it occurs? It occurs naturally. It is a natural process, like the virus mutation. You are seeing different types of virus, the Delta virus. All these mutations, they happen naturally. Antibiotic resistant bacteria also, they are happening naturally. But in case of bacteria, that mutation is much slower than in case of virus. However, if you misuse the antibiotics, or if you use the antibiotics, or if you are giving antibiotics where it is not required, then you can accelerate the process of resistance. Okay, the resistance process actually has been accelerated by us, by basically rampant use and misuse of antibiotics where it is not required, or you are not taking the full dose, or you are using it when it is not required. So we are basically accelerating the resistance. A growing number of infections today, such as pneumonia, tuberculosis, okay, gonorrhea, these are some dreadful diseases which are once they are thought that the mankind has conquered all these diseases, but they are coming back. In fact, tuberculosis is becoming has become a multi-drug resistant or extremely drug resistant. It is taking an extremely drug resistant form, and it's very hard to treat those type of tuberculosis. Okay. Then antibiotic, basically, it also, when there is this resistance issue, that means you have to go for very costly antibiotics, which are better, which are more having better activity, broad spectrum of activity. So basically that leads to longer hospital stays, and especially countries like us, it actually challenges or has a effect on the medical cost, so financial burden. Okay. Now, what happened? Because people are not very aware of this antibiotic resistance problem, so now this WHO, I think I will skip some of these slides. WHO has given reserved a week actually, World Antimicrobial Awareness Week, which many of us don't know. It is from 2015, this World Antimicrobial Awareness Week is a global campaign now that aims to increase the awareness of microbial resistance worldwide and to encourage best practices among the general public, health workers, and policymakers to avoid further emergence, because whatever limited arsenal that we have now, that will also will not work if we don't change our strategy. Okay, that's why this awareness week has started from 2015. Okay, and when it does take place from 18th to 24th November. Okay, so it's not far now. 16 days from now, the week will be declared as the, now the slogan is basically antibiotics. That was the slogan earlier, handle with care. Now it has changed to antimicrobials, handle with care. So there is a difference between antibiotics and antimicrobials. These are basically antibiotics is made by microorganisms to kill other microorganisms. Antimicrobials are a very general term which can kill any microbe. Okay, so antimicrobials, handle with care. That is the slogan. Every now student, every one of us should be aware of this. Okay, so this week is this 18th November 18th to 24th is the World basically Antimicrobial Awareness Week. Okay. Now let us talk about that. What type of different classes of antibiotics? We hear so many antibiotics. You go to doctor, the doctor sometimes prescribe erythromycin, azithromycin, sometimes some penicillin drugs, then cifran, ciprofloxacin, ofloxacin. There are so many different classes of antibiotics are there. Okay, how these different classes emerged? These classes emerged because of their structural variation, because of their target of action. So that's how the classification was made. And if you want to see, one important issue is that if you want to really take the battle against this bacteria, to challenge the bacteria to kill their resistance mechanism, you have to change the antibiotic, whatever is now current. Okay. Now, if you, that is not a very easy task, because you have to, where chemists actually have a very important role to play, because until and unless you know how antibiotics work at the molecular level, you will not be able to come out with new antibiotics. It will be very difficult to change the structural. That structural change is necessary, but how do you know that which structural change will lead to a new antibiotic? Okay, or which structural change will fool the bacteria? Okay, so that means you need to know the molecular mechanism of action of antibiotics. That is very important part from the from chemist's point of view. Okay, so that in order to know that, you need to know what is their target site of action. Target means, like, some antibiotics stop the production of proteins in bacteria. Some antibiotics stop the cell wall biosynthesis, because bacteria is protected. The bacterial cell is protected by a cell wall. So you have to develop a drug. Some drug actually target the cell wall formation in bacteria. Okay. Now, then cell wall, the question is then go to deeper level, that how cell wall is biosynthesized and how does the antibiotic stop the cell wall biosynthesis. Okay. Then only you can start developing new drugs, which can be called cell wall disruptors. Okay. And then you have to find that why the antibiotic has become ineffective, that what type of extra arsenal, what type of extra weapon the bacteria has developed so that it has become resistant. Okay, so that is another important area where chemists can play a role. Okay, and then once you know all these, then you can start thinking of what is your treatment options, what is the chemistry, what the chemist can do by doing structural variations. Okay, so basically it's a, if you look at all these things, it's a the chemist has a huge role to play to contribute to tackle this antibacterial resistance issue. Okay, now in very general sense, that if you take a bacterial cell, consider this as a bacterial cell. This is the cell wall, as you see that there is a wall, and inside liquid is what is called cytosol. Okay, and in the cytosol you have so many important ingredients like DNA, that is the number one ingredient. Then from DNA, you know that the message goes, it makes mRNA. Then from messenger RNA, proteins are synthesized. Okay, and in this whole process, there are function of so many small molecules are there, like folic acid, different vitamins, different cofactors, different enzymes. They all have a role to play. Okay, because everything, whatever is inside the bacterial cell, even including the cell wall, you should remember that everything is ultimately made by some enzymes. These are all enzyme mediated processes. Okay. Now, if you want to target, if you want to develop a antibiotic, it should target one of these machineries, whatever is there. And if this machinery, another important point is, if this machinery is different from the machinery that the human cell uses, then it will be much better, because then the drug will be much more selective. Because we also have this, now we also have DNA, we have RNA, we also synthesize proteins, we also utilize many of the cofactors, many of the enzymes, which are very common to the bacterial process as well as to the processes occurring in human cell. Okay, but there are certain things which are different, and many of these enzymes, although they function the same, but many of the enzymes are quite different structurally quite different from the humans. And that's why you can come up with drugs which are selectively targeting the bacterial cells. Now, if it is really not utilized by the human at all, then that drug will be the best, like penicillin. Penicillin targets the formation of the bacterial cell wall. Okay, so here I have listed many of these drugs, like cell wall biosynthesis disruptors. Okay, so that means molecules which stops the biosynthesis of the cell wall. So these will be very useful because because we don't have cell wall in our cells are protected by the membrane, that double layer, the fatty acid, the double layer. Okay, so this cell wall is unique to the bacteria. So these drugs are very, very safe in that sense. One of them is very famous, penicillins, then cephalosporins. All these are they target the cell wall biosynthesis. Okay, but as I said, that some of these machineries which also human use, but there are structural differences that are present. So you can selectively also kill bacteria targeting those type of machineries. Like some drugs are there which are also very common, tetracycline, streptomycin, then gentamicin, all these drugs, or chloramphenicol, chloromycetin, these actually stop the biosynthesis of proteins. They target the ribosome, which is called a protein making factory. And these drugs stop the biosynthesis of proteins. Okay. Then there are other various targets are there. You can target the biosynthesis of folic acid. You can target the mRNA. You can target the DNA also, like the ciprofloxacin. The DNA replication process can be stopped. So all these are there. So there are several targets that are present which you can exploit in making the antibiotics. Okay. Now, what happened that overuse of antibiotics, because the antibiotic discovery was specifically in 1928, September 3, when Alexander Fleming observed the existence of penicillin, although he didn't isolate. We'll go back to that. But from these 1940s, when penicillin was actually came into the market, see what happened over these 70, 80 years, these antibiotics have been used. So bacteria now, as I said, that every living organism had the right to live and they will hit back. So bacteria also has started to hit back, and they have developed different mechanisms to stop the action of these antibiotics. So what sort of mechanism they have developed? One is they have developed some enzymes, new enzymes, which destroys the antibiotic that is entering their cell. So that is one mechanism. That means they started making new enzymes which destroy the antibiotic, the very antibiotic that was earlier killing the bacteria. Okay. So before it can kill the bacteria, these enzymes destroy the antibiotics. So that is one. Another is they can actually have, very interesting, they can have what are called efflux pump. That means bacteria, the drug enters and then it is driven out through some pores. And so that's why these are called pumps. Like your pumps, you draw water, okay, or you drive water to fill up your overhead tank. So basically, this is efflux mechanism. The drug enters, and then there are pumps. These are chemical pumps, okay, not the mechanical pumps. Chemical pumps, which are driven by the energy obtained by hydrolysis of ATP. ATP hydrolysis gives energy, and through that energy, it operates the pump and drives the drug out. Okay, these are efflux pumps. And there are other different mechanisms by which the drugs have become ineffective. Okay, so they have modified the cell wall also so that the drugs don't enter. So all sorts of mechanisms the bacteria has developed. Okay. And see, this is the problem. As I said, this resistance is a very natural phenomenon, that whenever you have a collection of bacteria, okay, some of the bacteria, some of the few bacteria, bacterial cells will have some resistant mechanism already built in, okay, but they are few in number. The large number of bacteria that are there in this colony are actually very sensitive. So we call sensitive bacteria. Sensitive means which are killed by the antibiotic. And along with that, there will be few which will be resistant bacteria. But when you add antibiotic again and again, what will happen? The black ones which are sensitive, they will be killed. Okay. So ultimately, the red ones, they are resistant. So they will start now thriving. So this is the early stage and this is the late stage. So time and again, if you use the antibiotic, ultimately these red ones will start, because they are the only ones which will be left, and they will start thriving. And ultimately, you have a rapid growth of this resistant bacteria. Okay. If you had not given any antibiotic, where it is not required, so this would have continued like this. That is, will be mostly all these black dots, and there will be very few red dots. But when you challenge that system, so then the bacteria hits back, and ultimately the red ones will thrive. Okay. Now let us see a little bit about this, because students are there. I thought let us start that how this antibiotic development story. What is the story of development of antibiotics? Okay. Now, before there is a difference between antibiotics and antibacterial agents. That has to be also very clear. Antibiotics are basically made by microorganisms to kill other microorganisms, because everything is threatened by surrounding organisms. Okay. We are threatened by different animals. As we go to a forest, we are threatened. Animals are threatened by us. Okay. So bacteria is threatened by other bacteria. Fungi is threatened by other fungus. So everybody is trying to figure out something, make chemicals. So like that, the microorganisms make chemicals to protect themselves from outside anything. Okay. So this man, this gentleman, Sir Alexander Fleming, he was working on trying to get some antibiotics, okay, to develop antibiotics. And he was mostly interested in a molecule which are called lysozyme, which is basically a protein which has the ability to lyse the bacterial cells. Okay, lyse means just to burst they break down the bacterial cell wall. Okay, and the bacteria will be killed, and that is present in our tears, and in our tears that is present. And he was trying to isolate this lysozyme, and he was thinking that lysozyme is the cure for this bacterial disease. Okay, which is true, but the problem is to get enough quantity of this type of lysozyme is very difficult, and moreover it is a protein. At that time it was really not known, but now it is very clear that it is difficult to utilize a protein molecule as a drug. Protein molecule as a drug, because proteins should be metabolized inside the body. So that was the problem. But anyway, Fleming was working on this lysozyme. And basically, if one wants to see the antibacterial effect, they have to use what are called Petri dishes. If you have seen Petri dishes, it's a glass dish which also has a cover, a glass lid. And you have something inside which is called a matrix, made up of a jelly-like thing called agar-agar, and where you spray a little bit of bacteria, like you're making of cards. You add little card, and after a few hours, you see the whole milk has been converted into card. The same thing. So you add a little bacteria, spray, and then the bacteria will grow inside the plate. Okay. When bacteria grows inside the plate becomes hazy. Otherwise, the plate will remain clear if the bacteria does not grow. So this is a very easy way to check a chemical, whether it has got antibacterial activity or not. Okay, just by seeing whether it has generated a clear, whether the plate remains clear at some point and or it is becoming hazy. That means bacteria is growing. So Fleming was doing that. And what happened that during some of his when he was checking some of these plates, he found one of the plate was basically having a clear zone, and in the middle of that clear zone there is a fungus which was growing. Okay, that was basically the story of discovery of penicillin. It is accidental, quite accidental, but it also requires a mind to analyze things. Okay, many of these accidents actually are happening every day, but you need a rational mind, a clear mind, an intelligent mind to analyze and try to get things out of it, good things out of it. Okay, so Fleming did that. Okay, now before Fleming, I should mention, of course, two persons. One is Paul Ehrlich, a Nobel Prize winner in 1908. So he first developed an antibacterial agent which was called salvarsan. Those days, arsephenamine, that is the chemical name. It was basically, he was making many arsenic-based compounds, and out of 1,000 compounds, or more than 1,000 compounds, he found that the number 606, so he was giving number to every compound, okay, just to label it. And the number 606 compound is what is called salvarsan. It can treat many of the diseases, bacterial diseases. Okay, so that was the first example of what is called a magic bullet. This magic bullet theory was given by Paul Ehrlich because he was the person who believed that it is possible to develop a kind of a chemical which will be called the magic bullet. Why magic? Because it will go inside the body and only touch the bacteria and not the human cells. Okay, so his magic bullet theory was successful. He made these arsenic-based compounds, and that for some years that helped the onslaught of some of the diseases. However, these are extremely also toxic chemicals. Okay, remember, these are also, they will have a lot of side effects. Okay, about 20 years later, in our own city, Calcutta, okay, this gentleman, Sir U.N. Brahmachari, Upendranath Brahmachari, okay, he developed that medicine of Kalazar or the black fever, okay, and his drug was known as urea stibamine. Okay, this is, as students should know the history, that this is the perhaps the only drug which was discovered right in Calcutta. Okay, working at the Campbell Hospital. Campbell Hospital was now it is Nil Ratan Sarkar Hospital, NRS Hospital. So he developed this antimony-based compound. Okay, urea stibamine. So it's a combination of urea and this is the stibanilic acid. That is the, if you hydrolyze this will be OH, and that will be stibanilic acid. It's a combination of stibanilic acid and this urea, and that worked miracles in treating the Kalazar. Okay, Sir U.N. Brahmachari. And later on, after 1930s, remember, just before 2 years before 1930, Fleming observed the occurrence of penicillin, but he could not isolate penicillin, so it was not introduced into the market. But before that, Paul Domag, he got the Nobel Prize in 1939. He developed a molecule which is called Prontocil, the first commercially available antibacterial agent. Again, this is actually not made by a bacteria. This is a synthetic compound. So it's called an antibacterial agent. And these sulfur drugs, they have a particular mechanism. Everything is now known how they work. Just in short, I think the next slide shows that they actually stop the folic acid biosynthesis in bacteria. Folic acid is an obligatory coenzyme which is required for one important conversion, I can tell you, like conversion of uracil into thymine. Uracil is the base present in RNA, and thymine is the base present in DNA. But this thymine comes from uracil, not exactly from uracil. Uracil connected to a sugar and then a phosphate. Okay, so that is a nucleotide, and so that is converted. This uracil is converted to thymine. So that important process requires folic acid as a coenzyme. So folic acid biosynthesis is stopped in bacteria. Just to again, one important point to mention here is that we humans cannot synthesize folic acid, but folic acid is synthesized by bacteria. And bacteria, the interesting point is bacteria cannot utilize folic acid from outside. On the other hand, humans cannot synthesize folic acid, but we get folic acid from our diet. Okay, so this is a good target. If you stop the biosynthesis of folic acid in bacteria, then you get an antibacterial agent. Okay, and that is exactly what happened. Antibacterial agent action of the sulfonamides were due to the stopping of biosynthesis of folic acid. So this is that famous plate of Sir Alexander Fleming, and this is how it looks, as I was telling, that if bacteria grows, then this will be hazy. The space where bacteria does not grow, that remains clear. Okay, so that means you have a chemical which has been added here, and that is killing the bacteria. And the greater the zone, the size of the diameter of the circle, provided you have given same concentration of all materials, you can actually also evaluate the relative antibacterial activity of these molecules. Okay, so that was Fleming's observation. Fleming tried many times. He was a microbiologist. He tried to isolate penicillin, but penicillin molecule is very, very sensitive, very unstable. So he could not isolate penicillin. And within 3 years, he lost interest on penicillin. And he published only 2 papers. And then he started working on his lysozyme, I told you earlier. Okay. Then what happened? World War started in 1939, and there was a renewed effort that we should come out, that the world should come out with the discovery of some very good antibacterial agents. Okay, because Prontosil, which was developed by Paul Domingue, was not serving the purpose. Okay, we need a better molecule. And then at University of Oxford, Flory and Chain, these 2 scientists, they saw Fleming's paper, went back to Fleming at London, and then got the strain which was making the penicillin, and they were able to isolate the penicillin. And ultimately that came into the market. Okay, and these 3 persons got the Nobel Prize in 1945. Okay, and along with that, there were other contributors who didn't discover the penicillin, like Dorothy Hodgkins. She proved the structure of penicillin by X-ray crystallography. John Sheehan at MIT, he chemically synthesized the first chemical synthesis of penicillin. And Jack Baldwin, he discovered the enzyme which makes the penicillin in the microorganism. Okay, so all these people contributed to the development of penicillin. Now, interestingly, what happened, that let me try to shorten yes. During every Nobel Prize winning ceremony, the prize winner has to give a lecture. So Fleming was delivering a lecture. And towards the end of his lecture in 1945, he ended up by saying that, but I would like to sound one note of warning. Penicillin is to all intents and purposes non-poisonous. So there is no need to worry about giving an overdose and poisoning the patient. Because if you can give overdose, that is still not a problem because it does not affect the human cells. There may be a danger, though, in underdosage. It is not difficult to make microbes resistant to penicillin. in the laboratory by exposing them to concentrations not sufficient to kill them. And the same thing has occasionally happened in the body. So basically, I will not elaborate further, but in 1945, Fleming himself, the discoverer of penicillin himself, warned the world about the existence of resistance. Okay, so he said if there is an underdose or the concentration is less, then there will be a problem. The microorganism can develop resistance. Okay. Now let us again a little bit go back. The question is how penicillins work, because if you want to now really stop the overcome the bacterial resistance of penicillins. Now really penicillins really don't work. Doctors don't prescribe penicillins, only penicillins. Like there are amoxicillin, ampicillin, whether you have heard these names, cloxacillin. They have lost their potency. Okay. Unless they are combined with another drug. I will also talk about that. Okay. Now penicillins, actually I told you that there are drugs which have many targets. Penicillins target the formation of the bacterial cell wall. Okay. Bacterial cell wall, which is different from the cell membrane that we have. Okay. So it's very specific for the bacteria. And now what is bacterial cell wall? Interestingly, bacterial cell wall is like these rods. You are seeing these blue rods or blue chains. And then there are the hanging, pendant, some wavy lines. Okay. These are nothing but peptides. And these blue things are nothing but, they are called Glycan units. They are made of sugar units. They are combination of various polymeric combination of sugar. So there are these rods, they are like beams, and then the beams you have you have columns. Okay, you know, when you make a house, the house becomes very strong when you connect these columns through beams. That is how the houses are made. Okay, if you take a very simple example, everybody knows how the vulcanization of rubber is also, it made how the tire was made. The rubber had to be made strong. So what you do, you made cross-linking with the help of sulfur. Okay, sulfur cross-linking of the different this poly isoprene chains. Okay, so it's the same thing. Bacterial cell wall made up of Glycan units, and then there are these hanging peptides, and these peptides are being cross-linked. Okay, unless they are cross-linked, the cell wall is not very strong, and they will just burst open because the inside pressure is very high. Okay, so they will burst open, and penicillin stops this cross-linking. See here, the cross-linking is shown. These are the hanging, these are the side chains, and the cross-linking is basically joining of these side chains. So this is how these columns are connected. Okay, the penicillin stops the formation of these cross-links. Okay, that is in simple terms. Okay, I'm not going. Okay, let me see. What is the side chain? The side chain is nothing but glycine units. Okay, in gram-positive bacteria. And what is the other hanging chain? The other hanging chain is basically the terminal amino acids are interesting. Alanine. There are two alanines. D-alanine. Look at the configuration. You know that all the amino acids that make our proteins, they belong to L amino acids. In bacteria, you have this D-alanine as a part of these peptides. So what happens? The cross-linking reaction is nothing but replacement of one of this D-alanine peptide, one of this D-alanine amino acid from this peptide, and it is replaced by a glycine. That means this glycine is now connected to this D-alanine, the penultimate one, and the terminal one just leaves. So it's a basically transpeptidation reaction, because you have different trans-esterification. You remove one alcohol of the ester, replaced by another alcohol. So this is called transpeptidation. You replace one amino acid with another amino acid. But in the process, you make this cross-link. Okay. How penicillin stopped this process? Very interesting. If you start writing the structure of these penicillins, and if you start writing the structure of this D-alanine, what you will see that this is written here. Maybe I can use that. See, this is your D-alanine. That means their configuration is D. Okay. So you write D-alanine in this fashion, and this is what is the structure of penicillin. Not very complicated. Basically, it is quite simple. It has got this 4-membered ring and a 5-membered ring. But if you start looking at D-alanine, and write it in this form, which is called a conformation, by the way, if I write this conformation and you write penicillin, you will see that this part resembles the part which is present here. So basically, penicillin mimics the D-alanine. So what will happen? That when this enters the bacterial cell, so bacterial cell is supposed to do this reaction, recognize D-alanine, but instead, because penicillin looks like D-alanine, so it takes penicillin, mistakes. It does a mistake. It thinks that penicillin is the D-alanine molecule. And then it accepts that and reacts with penicillin. And that's how the enzyme does not work, because it is now picking up a wrong molecule rather than the right molecule. So in simple terms, that is how penicillins work. So you can say that it stops the transpeptidation reaction, which brings up the cross-linking. And how it does? Because it mimics the D-alanine, which is recognized by the enzyme. But penicillin has a structure which is very similar to D-alanine, and then the bacteria, the enzyme by a mistake thinks that penicillin is the substrate, and then reacts with penicillin. And once the reaction takes place, the enzyme becomes inactive. Okay. Then what happened? Bacteria became very clever. Okay. So earlier what happened? I was telling that penicillin, in simple terms, I can write here, penicillin plus the enzyme. Okay, let us call that enzyme 1. Okay. So that reacts and you get a penicillin. It will not be penicillin, it will be some transformed, because the reaction has taken place. Transformed penicillin, which is connected to the enzyme 1. So enzyme 1 cannot function now. So that is basically inactivation. Okay. Now so bacteria, what happened? Bacteria was so clever, it now started making another enzyme, which we call enzyme 2. Okay. And this enzyme 2 is more efficient than enzyme 1. So efficient means it can recognize penicillin to a much more better extent than the enzyme 1. So it will now react with penicillin, this enzyme 2, penicillin, and then it will, because it reacts, so that will be a transformed penicillin again, the same reaction, but it is done by enzyme 2. But the enzyme 2 has the ability to break this bond. So when it breaks the bond, it releases itself from the transformed penicillin, and what you get is a transformed penicillin. Unfortunately, this transformed penicillin does not have any antibacterial effect. It is no antibacterial effect. So basically what happens, if you take penicillin and if the bacteria has both these enzymes, enzyme 1 and enzyme 2, so enzyme 2 being more efficient, it will react with penicillin and destroys the penicillin. Basically, it is destroying the penicillin and making it inactive. So that started happening. Hello? Any?
No, sir. Continue.
How much time I have? Let me see. Okay, maybe 10 minutes. Huh? Is it okay? 10 minutes?
No, sir. We continue. You continue, sir.
Okay. Okay. Then what happened? See, I am telling you like a story, so I don't know how it is working. So what happened? This penicillin was becoming ineffective. What exactly Sir Alexander Fleming pointed out at that time, right in 45. And in fact, when 45 it was introduced, 5 years later, they found that the first penicillin which was introduced into the market was penicillin G and penicillin B. They started losing their activity because of the emergence of these second enzyme I was talking about. Okay, the second enzyme has a name. I am actually not telling you the name, but now let me name these enzymes. It is called a beta-lactamase, because this is a ring which is called a beta-lactam ring, because any cyclic amide is called a lactam. Like any cyclic ester is called a lactone. Similarly, cyclic amide is called a lactam. Okay, penicillin has a 4-membered ring, so that is called a beta-lactam. And this enzyme, second enzyme, destroys. This is the breakdown of the penicillin, the transformed penicillin I was talking about. So this bond is broken. If this bond is broken, then you get this compound. This does not have any activity. Okay, so that's why this is called a beta-lactamase enzyme, because it is breaking the beta-lactam. The first enzyme is what is called a transpeptidase, because that does a transpeptidation reaction. Okay, so this is the emergence. 1960s, that beta-lactamase started emerging. But what happened at that time? The scientists were making new forms of penicillin. If you look at the structure of penicillin, this is what is called the pharmacophobe. Pharmacophobe means this is the actual important structural moiety that gives the activity. But there is one R here. So you can actually change this R. This is a very simple reaction. You can have the amine, do acylation, different R's here, okay? Like phenyl, chlorophenyl. So thousands of molecules were made. And out of these first came the ampicillin, then came the amoxicillin, then came methicillin. So these are all different penicillin molecules with a different R. So that actually basically rescued the people in the 60s, 70s, and 80s by varying this group R, okay? But then ultimately they ran out of any option here, because all the possible R's, whatever group you can think of, have been made, okay? So that strategy ultimately didn't work, it failed, okay? So then they realized that, because whatever you are actually, basically what you are doing, you are not changing the actual chromophore, you are changing only the side chain. Means if you want to change a person's mentality by putting a new shirt, new clothes, that does not change the person's mental method. Okay. So it's the same thing. This is the actual reactive part. So if you change R, it will work a little bit, but ultimately that strategy will fail. So that strategy ultimately is not working today. And nobody prescribes ampicillin, amoxicillin, methicillin, fluoxacillin by itself. Okay. So people started working, or chemists started looking at that, how to, first of all, what is the mechanism of this reaction? How it hydrolyzes. This is nothing but hydrolysis reaction. This is NH, that is OH, hydrolysis. So how this hydrolase enzyme, beta-lactamase, works, that is number one. And then if you know the mechanism of working, then you can start developing another molecule. See, now basically, if you want to make penicillin to work again, like previous years, what you have to do, you have to challenge both the enzymes. Enzyme 1, which is a transpeptidase, as well as enzyme 2, which is a beta-lactamase. So you need 2 molecules now. One strategy could be 2 molecules. If you have a molecule which can tackle both, that is very good. But other strategy will be that you have two molecules, one targets this, another targets this one. Okay. So actually this second strategy worked quite well till about 10 years back. Now we are running again another risk. So let us see how it developed. Once people identified the second enzyme, different pharmaceutical companies, they started looking at molecules, different molecules which target the second enzyme. Remember that beta-lactamase. And what they came out, actually, again, it is nature, Mother Nature, who gave us a molecule, which is called clavulanic acid. The structure is like penicillin, but it is not penicillin. There are some differences. This is what is the structure. Okay. It again has this beta-lactam. It again has a 5-membered ring, but it is, instead of sulfur, it has got oxygen. It does not have any side chain here. At this point, there is no side chain. And it does not have this gem dimethyl, which is present in penicillin, gem dimethyl, but it has got some double bond, something is there. But interestingly, this molecule is a very good inhibitor, means basically it stops the action of enzyme 2. Enzyme 2. So what is this enzyme? This is that beta-lactamase. Okay. Beta-lactamase enzyme. So it was basically a miracle. Nature saved us at that time. 1976, it was discovered, and then ultimately it was isolated in large amount by fermentation. And today, a life-saving drug is what is called augmentin, which is a combination of amoxicillin and clavulanic acid. Okay, so you understand a little bit of the chemistry, that this targets the enzyme 1, which is the transpeptidase enzyme, and this targets the second enzyme, which was earlier destroying the amoxicillin. Okay, I think there are some mechanisms here which is shown here. If students are interested, they can read about how clavulanic acid works, what types of different inhibition processes are there. There is a very interesting term which is called suicide inhibition. That means the enzyme is committing suicide. The beta-lactamase enzyme is committing suicide in the presence of clavulanic acid. But anyway, this was a wonder drug, the combination of the two, and that is still saving millions of lives. Okay. Now, as I said, the bacteria will not sit back. Okay, they found that okay, the humans now have come out with another molecule, clavulanic acid, which is killing the enzyme 2. So let me change the enzyme 2. Miss, I am talking on behalf of the bacteria. So they changed the enzyme 2. They changed the enzyme 2 by changing the hydrolysis mechanism. By changing the hydrolysis mechanism. Okay, let me see whether the hydrolysis mechanism is there. Maybe there. Just a second. Not here. Maybe I can. Okay. I can write. That will be better. So basically what was happening, that the enzyme 2 was breaking down the penicillin. Okay. Was breaking down the penicillin. Now, if as a student of chemistry, let me just put X here. Okay. You know that hydrolysis reactions can be catalyzed by acid, or it can be also mediated by bases. Okay. So here, in case of enzyme catalysis, there are, in the enzyme side, there is a nucleophile, okay, in the form of an amino acid called serine, okay, which has got a wedge. And this wedge is the one which attacks the carbonyl and ultimately breaks it. So this is the mechanism of the second enzyme. So it has got a nucleophile. The nucleophile breaks down the amide bond, okay. Not difficult to understand, okay, phenyl, this wedge. Serine is a nucleophile, the which is a nucleophile. Now, when this clavulanic acid came, the enzyme started changing itself. So it came out with another enzyme, okay, enzyme 3. How it hydrolyzes? It also do the same reaction, but not through serine. You know, as I said, any hydrolysis reaction can be catalyzed both by acid as well as base. How acids catalyze? Acids catalyze by chelating to the oxygen, like a metal ion. And then if you chelate to the oxygen, there will be now, this bond will be weakened and this carbon becomes more electrophilic. So when the metal ion chelates to this oxygen, this carbonyl carbon becomes more susceptible to nucleophilic attack. And simple water, which is present inside the active site of the enzyme, that comes and hydrolyzes the NH. Okay, so this is now this is what is called a metallo-beta-lactamase. Okay, or a metallo-protein, metallo-enzyme you can call. Okay, because I think in the inaugural when they started, Vidhan said about metal ions, no, cisplatin. Metal ions play a major role in various ways in giving us drugs and also in many enzymatic reactions. Metalloenzymes are there, and like one of these is here. The metal ions chelate to the oxygen and water comes, simple water, now hydrolyzes the beta-lactam. So instead of serine, you see there is a change in the mechanism. And this metal ion is, by the way, is a zinc metal ion. Okay. So now we have a task. The enzyme has changed the mechanism. It has become enzyme 3. It is a metallo-beta-lactamase. Now it utilizes the metal ion. And remember, it does not utilize the amino acid residue in the enzyme. Earlier, clavulanic acid was targeting to inactivate these enzyme residues. Now the problem is the enzyme directly is not involved. It has got a zinc ion as a cofactor, and the zinc ion chelates to the oxygen, and water comes and hydrolyzes the beta-lactam. Okay, so you see there is a complete change in the mechanism of the reaction, and that is the story today. Metallo-beta-lactamase are extremely difficult to treat. We don't have much option today. There are few drugs still available which can stop the onslaught of the metallo-beta-lactamase. One metallo-beta-lactamase, and see, this metallo-beta-lactamase is also changing. Now we have different metallo-beta-lactamase. Metallo-beta-lactamase 1, 2, 3, 4, 5, 6. All are changing. Like the virus, we have alpha, beta, gamma, delta, the COVID. So these metallo-beta-lactamases there are now 15 metallo-beta-lactamases, gene dependent, which are available or which are not available, which are there in the in different parts of the world. Okay. Unfortunately, this advent of this new metallo-beta-lactamase, which was first named as New Delhi metallo-beta-lactamase producing enzyme, NDM, but because it was claimed to have been originated in New Delhi, but then our government, actually this is not a very gentle way to name a bacteria, because it should not be tied up with the place, okay? Because it can happen to anybody, any place. Like COVID is not connected to China. Huh? It has got a biological name. So I think Indian scientists have objected, government had objected. But it is still in the literature. They are saying it as New Delhi NDM producing beta-lactamase. Okay, it somehow started in Delhi. Okay, it could have started anywhere in the world because of the use of antibiotics. But anyway, this NDM producing bacteria is very dangerous, especially the gram-negative bacteria. And you should know that many of these COVID-related deaths are basically happening due to secondary infections of the lungs. And many of the infections are being done by an organism called Klebsiella pneumoniae. Klebsiella pneumoniae actually has this NDM. Now they are having this NDM producing mechanism and none of the antibiotics are working. So we are now facing this danger. So what will be our option now? Try to find out a new drug. Okay. Remember, NDM uses what? A zinc as a metal ion. It's a metallo enzyme. Okay. So there are two strategies. One, you can target the metal ion, some molecule which targets the metal ions. The other is you target the active site amino acid residues, which is holding up the zinc and the water. Okay, remember, this process is done by zinc ion, activated by zinc, and then water comes and happens. Okay, so somehow you stop this process. One, that you target the metal ion, or the other is you target the amino acid residues inside. Okay, targeting metal ion is a little bit difficult because there are so many zinc related, zinc dependent enzymes which are inside our body. So finding a selective zinc chelating agent will be very difficult. Like this, I know these NDMs are killed if you add EDTA, ethylene diamine tetraestic acid, which is a very good zinc chelator. But the problem is EDTA will be very non-selective. If you mix amoxicillin with EDTA, the EDTA will now stop other important enzymes inside the body. Okay, so that is problem. However, if there is a difference in the structural pattern, you can have specific, because there are people who are trying to develop specific molecules which can only chelate to the zinc ion present in the metallo-beta-lactamases. Okay, that is one strategy. The other one is that whenever somebody is having an infection, you go to the doctor. How the doctor knows that this infection is by an organism which is producing metallo-beta-lactamase? Either you do a culture, which culture takes about 72 hours to find out which antibiotics ultimately work on it, or you should have a quick assay system to know that yes, this is an organism which is producing metallo-beta-lactamase. Because if it is infection caused by an organism which is not by metallo-beta-lactamase, then no point in giving very high-end superactive drugs. That is not needed. It all depends on the enemy. No? If the enemy is weak, you use your weak weapons. If the enemy is strong, you try to use your strong weapon. Because remember, if you show your strong weapon once, the whole world will know that you have this as your last resort. That should not be divulged very quickly. That should be divulged only when it is required. Okay. So there are two aspects. One is how to identify very rapidly that is somebody suffering from this infectious disease caused by resistant organism, especially the metallo-beta-lactamase producing bacteria. That is one. And the other is how to really make a drug which stops this metallo-beta-lactamase. Okay. So these are some of the issues that are very important. I think time is running out. Yes. Proloy, I think it is.
Yes, I mean, sir, you can maybe finish in a couple of minutes, sir.
Couple of minutes, okay. So I will not elaborate like, because whatever work has been done in our laboratory, we have actually come out with a system, diagnostic system, which can rapidly identify that whether this NDM enzyme is present in the bacteria that is causing the infection or not, very rapidly. The problem is actually very huge because it's basically you are catching a fish, you are trying to catch a particular fish in a system, in a pond or a river or sea where lots of other fishes are there. If you want to catch only hilsa fish, it's very difficult because this fish hook is not selective. Nah? Any fish can be caught by this mechanism. If you want to really know the presence of a particular fish, you need to have a fish hook which is very selective for a particular kind of fish. It's the same challenge that you have. If you want to detect the presence of a particular enzyme in a setup where there are many enzymes are present, so you should have a particular fish hook. In our case, it's a chemical hook, which will be only recognized by that particular enzyme. Which enzyme we are talking about? We are trying to detect the metallo-beta-lactamase presence. And so there are different strategies by which you can have this chemical hook. Because there are, first of all, the hook has to be there, which will be recognized by the enzyme. Then you should have a way to really know which enzyme has been caught by your hook, by your chemical hook. Okay, so there are fluorescence-based strategies, which will guide you that which molecule has been trapped by your tissue. So just by using that strategy, it's a fluorescence-based strategy. So your molecule, basically the chemical hook, has several components. One is it is attached to a moiety, which is recognized by your enzyme, the target enzyme. Then you should have a chemical functionality which will react, which is called a cross-link, which will immediately fix it to the to your probe. And then you should have a fluorescence moiety in the molecule, which will allow you to ultimately, by doing a fluorescence imaging, fluorescence electrophoresis, you can identify which protein has been identified. Okay, like, see, just 1 or 2 minutes. If you have a molecule like this, suppose this is a molecule, which is a benzene ring. See, you see it is attached with an azide moiety. You know the azides by shining light from nitrine, and nitrine can react with, it's a very reactive species. So it will react with the amino acids in the protein. So that makes the cross-link. It has got this green circle, a green sphere, which has got this what is called pharmacophobe, which is recognized by the enzyme. And it has, in addition, it has got a fluorescence molecule, moiety, which will ultimately tell you whether this molecule has gone inside the protein and made a cross-link with the protein. So this is basically the strategy. So even if you have many proteins, like here you are seeing at least 3 proteins, and then some other small proteins here, fragments are there. Okay, so 3 proteins, but if your molecule probe is very selective, it will react with only 1, and this is the fluorescence image of this gel electrophoresis. So you see the bands. So from these bands you compare and you can identify which protein has been trapped. Okay, so this is the principle behind this, how to locate or how to identify the presence of a particular protein. But remember, this is not easy task. Your probe has to be very selective. Number 1, the probe should have 3 components. One is the recognition component, the enzyme recognizes. The other is the cross-linking component, where you shine light and there is a reaction. And third is the visualization component, which is the fluorescence moiety. Okay, these 3 has to be crafted in a molecule, and then ultimately you can come out with different probes. And we have done that, and we have ultimately been successful in making compounds which can detect, which can detect the, I'll just, so many slides are there, which can detect the presence of New Delhi metallo-beta-lactamase. Now we have changed in our papers, we don't call it NDM, we call it PCM, penicillinase or PDM, penicillin destroying enzyme, in order to avoid this NDM. We don't want this name. Okay, as I said, it can originate anywhere, like COVID-19, originate in China, but it is not associated. The name is not associated in China. Okay, so anyway, this enzyme now we can identify within a span of, I can say within a span of 2 hours. You can identify the presence of NDM. You can identify, in fact, this probe that we have developed can identify in principle different enzymes by changing that recognition hand. Change the recognition hand and do the experiment. You can identify another target enzyme. Okay, I think I will not elaborate any further. These are some of the molecules. See, as chemists, ultimately, it boils down to making molecules. So we made molecules, and we have been extremely successful in making making the diagnostic assay system to diagnose the presence of NDM. Like this is a clinical sample. So many enzymes are present. But if you look at the fluorescence imaging, only this enzyme is being trapped. And this is what was found to be the metallo-beta-lactamase. Okay. The molecule has been shown here. This is what is the molecule number 2. That is the molecule we have made. So I think the battle is still on. What we have come out with a diagnostic kit, how to identify rapidly the presence of this metallo-beta-lactamase, but still the world is searching for the how to find an inhibitor for the metallo-beta-lactamase. Okay, because clavulanic acid is for the enzyme 2, which is a serine-based enzyme. Okay, remember that. So clavulanic acid is not working against this metallo-beta-lactamase. So with these, I think I gave you many the latest situation. The solution is not there. It is only the young people, the researchers, they know the problem. So I wish that some of you take up research in this area and try to come out with new drugs, new ways of treating antibiotic resistance. Okay. So I think I will stop here. These are the acknowledgement. I didn't actually elaborate my work, but all this work, always remember that today is the time of collaborative research, because for one person to do all this is extremely difficult, because we are trained as a chemist making molecules, mechanistic, but we need to know how to do these electrophoresis, how to generate bacteria, how to clone enzymes, all these things. So you have to now intimately collaborate with biologists. Okay, so there are many, these are my students and scholars, but there are other professors, you see, they are all biologists, and I always collaborate with them in order to proceed further. Okay, so I think, thank you very much for listening to the lecture, and to the students especially, don't think like this research is an easy task. It's a very difficult one, but it ultimately, the end result will satisfy you definitely. It's a zigzag path, ups and downs, but ultimately, if you stick to the problem, don't elaborate many things, don't tackle many things at the same time. Ultimately, you will be successful. Okay, thank you very much.
Okay. Thank you, sir. It's a very interesting, popular talk, and I think all of us enjoyed, starting from the history and then gradual development, and then how the mechanism it works, and then cells, laboratories, new discoveries. So it's very interesting. So now it's open. Maybe sir can take a couple of questions or queries. So feel free to ask.
Yeah, feel free. Even in Bengali, if you ask, no problem. বাংলায় যদি কেউ বলতে চায় বাংলায় জিজ্ঞেস করতে পারে। স্টুডেন্টরা আছে?
স্যার কারো কোশ্চেন মনে হয় নেই তো স্যার, মানে I have a very simple questions, and now আমার এখন ডাক্তারবাবুরা সাধারণ জ্বর হলেও মানে নট এটা যে ব্যাকটেরিয়াল ইনফেকশনস, কিন্তু তা সত্ত্বেও একটা অ্যান্টিবায়োটিক দেন, এবং সেটার কারণ হিসেবে বলা হয় যে এটা সেকেন্ডারি ইনফেকশনসটাকে সাপ্রেস করতে পারে। হ্যাঁ, মানে সেইটা কতটা তাহলে মানে এটা ইফেক্টিভ, মানে এটা কি সত্যি সত্যি তাহলে এফেক্টিভ, কিন্তু তাহলে ইট ক্যান গো টু দি আদার ওয়ে অ্যারাউন্ড।
এটা ভেরি গুড কোশ্চেন। আমি তোমাকে বলছি আমার নিজের এক্সপিরিয়েন্স। আমি যখন ইংল্যান্ডে গেছিলাম, ওখানে তো ওয়েদার খুব স্যাঁতস্যাঁতে, বৃষ্টি হয় খুব। আমি গিয়ে আমার খুব থ্রোট ইনফেকশন হতো প্রচন্ড। হ্যাঁ, থ্রোট ইনফেকশন হতো। আমি ডাক্তারের কাছে যেতাম, আর ডাক্তারবাবু আমাকে বলতো যে খালি ডিসপিরিন জলে গুলে একটু গরম জল দিয়ে গার্গল করবে, ব্যাস, আর কিছু না। এরকম চলছে, 1 মাস হয়ে গেল, 2 মাস হয়ে গেল, কিছুই হয় না। তখন ডাক্তারের কাছে গেলাম। আমাদের দেশে কি হলো, অ্যান্টিবায়োটিক দিয়ে দিত। আমরা ভাবতাম যে অ্যান্টিবায়োটিক দেবে আমার সেরে যাবে। তা আমি ডাক্তারকে গিয়ে বললাম, আই ওয়েন্ট টু দ্য ডক্টর অ্যান্ড সেড দ্যাট হোয়াই ডোন্ট ইউ প্রেসক্রাইব দ্য অ্যান্টিবায়োটিক। ওখানে তো অ্যান্টিবায়োটিক ইউ ক্যানট বাই অ্যান্টিবায়োটিক ফ্রম দ্য স্টোর আনলেস দ্য ডক্টর প্রেসক্রাইবস। তা কি হলো, ডক্টর আমাকে তখন হাসলো। হি স্মাইলড অ্যাট মি and then he said, okay, you want, I am giving you, but you will be back after 10 days. যতক্ষণ ভাইরাস requires a host, ওকে। তা আমি যদি যে ব্যাকটেরিয়া গুলো তোমার শরীরে আছে, হেল্পফুল ব্যাকটেরিয়া, কিছু ভাইরাস তাদের উপর বেস করে বেঁচে আছে, এবার সেগুলোকেও মেরে ফেলবো, তখন সমস্ত ভাইরাস তোমার শরীরে গিয়ে পড়বে, ও বেঁচে থাকবে তোমার শরীরকে নিয়ে। সুতরাং ইট উইল মেক দ্য সিচুয়েশন ওয়ার্স। আমি তাও জোরাজোরি করাতে আমাকে ডক্সিসাইক্লিন দিল, ডক্স যেটা, ডক্সিসাইক্লিন দিয়েছিল। তা আমি তো খুব আনন্দ যে অ্যান্টিবায়োটিক পেয়েছি, খেলাম। প্রথম 2 দিন মনে হলো ভালো আছি, সাইকোলজি হতে পারে সেটা। তারপরে আবার 7 দিন বাদে দেখি ব্যাক টু স্কোয়ার ওয়ান। ঠিক আছে, এবার আবার ডাক্তারের কাছে গেলাম, আমাকে বললো যে হি সেড, আচ্ছা ইন দ্য মিন টাইম ওরা কিন্তু সোয়াব টেস্ট করেছিল। এই যে সেকেন্ডারি ইনফেকশন আমরা ধরে নিয়ে দিচ্ছি, ডাক্তার যেটা দিচ্ছে সেকেন্ডারি ইনফেকশন, এটা কিন্তু উইদাউট টেস্টিং করাটা ঠিক নয়। আমাদের দেশে একটুখানি সেকেন্ডারি ইনফেকশন একটা চান্স আছে ঠিকই, কারণ এখানে আমাদের অ্যাটমসফিয়ার যা, এখানে ব্যাকটেরিয়া খুব তাড়াতাড়ি থ্রাইভ করতে পারে, এটা ঠিক। কিন্তু বেশিরভাগ ক্ষেত্রেই আমার মনে হয় ওটা দেওয়াটা ঠিক নয়। সেকেন্ডারি ইনফেকশন আটকাবার জন্য মানে কি, আমার যদি না হয় আমি আটকাবো কেন? আমার যদি হয় তখনই তো আটকাবার প্রশ্ন। ওটা যদি ঠিক মতো 3 to 4 days বা 7 days অব্দি দেখা যায়, তারপরেই যদি কেউ দেখে যে না জ্বর এসছে এখনো, কিন্তু তাও কালচার করে মানে কিছু টেস্ট করে এটা করা উচিত। এটাতে কি হচ্ছে, আমাদেরও ধারণা হয়েছে ডাক্তার যদি অ্যান্টিবায়োটিক না দেয় আমার সারবে না, দিতেই হবে। আবার ডাক্তাররাও জানে যে এই লোকটা আমার কাছে আসবে আমি যদি অ্যান্টিবায়োটিক দিই। এই একটা চলছে, মানে কোনো মানে এই সেকেন্ডারি ইনফেকশনের ভয় দেখিয়ে চলছে, এটা ঠিক নয়। কারেক্ট, আনলেস ইউ হ্যাভ প্রুফ যে হ্যাঁ দেয়ার ইজ এ সেকেন্ডারি ইনফেকশন। বেশিরভাগ ক্ষেত্রেই ভাইরাল ইনফেকশন। এই করেই রেজিস্ট্যান্সটা আরো এসে যাচ্ছে। এটা একটা। আরেকটা হচ্ছে র্যাম্প্যান্ট ইউজ ইন তোমার অ্যানিম্যাল ইউজ। ধরো ব্রয়লার, এই যে বিভিন্ন মুরগি যেখানে পালন হচ্ছে, যেখানে সেখানে প্রচুর অ্যান্টিবায়োটিক ইউজ হচ্ছে, সেগুলো কিন্তু প্রচুর তোমার রেজিস্ট্যান্স নিয়ে চলে আসছে। অ্যান্টিবায়োটিক ইউজ হচ্ছে, এইটাই প্রবলেম। আমার তো কোনো অ্যান্টিবায়োটিক এরকম স্পেসিফিক নেই যে একবারে অ্যানিমালের জন্য এইটাই, মোটামুটি কাছাকাছি। হয়তো অ্যাম্পোটেরিসিন বি হয়তো কোনোটা কাউকে দিচ্ছে, কাউকে অ্যাম্পোটেরিসিনটা মেইনলি অ্যানিমেল ওটাই দেওয়া হয়। তো সেটা ইভারমেকটিন দুটোই দেওয়া হয়। এখন তো ইভারমেকটিন কোভিডেও দেয়, আবার অ্যানিমেলকে অ্যান্টি ড্রাগ। বুঝতে পেরেছো? বোঝাতে মানে ব্যাপারটা হচ্ছে এটা, যে ওটা উইদাউট টেস্টিং করা না করে দেওয়াটা কোনো মানেই হয় না।
আমাদের মনে হয় যে আমাদের রেগুলেশনটা মানে নেই, যার জন্য এইগুলো প্রবলেম, যে বাইরে
তারপরে কি একটা যে কোন অ্যান্টিবায়োটিক সেটাও তো ইম্পর্টেন্ট। তুমি যদি প্রথমেই তোমার আমি যেটা বললাম লাস্ট ওয়েপেনটা যদি প্রথমেই দিয়ে দাও, ঠিক আছে, প্রথমে ওই কম্বিনেশনটা দিলে অগমেন্টিন, যেটা দরকার ছিল না হয়তো তখন, এই একবার দিয়ে দিলে নেক্সট রাউন্ডে যখন তোমার সেই ইনফেকশনটা যদি আসে, তখন তোমার হাতে আর কোনো অস্ত্র নেই, শেষ অস্ত্র দিয়ে দিয়েছ। সেটাই একটা। বাট দুটো ডেঞ্জার আছে, আরেকটা হচ্ছে এই সিলেকশন অফ দি অ্যান্টিবায়োটিক।
ঠিক আছে।
আচ্ছা, আর যদি কারো কোনো কোয়ারিজ থাকে তাহলে।
হ্যাঁ স্যার, আমার একটা জিজ্ঞাসা, লাস্টের কথাতেই আমার জিজ্ঞাসা আর কি। অ্যান্টিবায়োটিক যখন দেয়া হয় তখন কোর্সটা কমপ্লিট করতে বলা হয়, আদারওয়াইজ এটা রেজিস্ট্যান্ট হয়ে যায়। রেজিস্ট্যান্ট হওয়ার ব্যাপারটা মানে মেকানিজমটা কি, মানে ওই ওষুধটা পরে আর কাজ করে না, ড্রাগটা রেজিস্ট্যান্ট হয়ে যায় তো আর ব্যাকটেরিয়া, এটার মেকানিজমটা কি? মানে
এটাই তোমাকে মেকানিজম বলতে, ব্যাকটেরিয়া উইল কাম আউট উইথ with so many changes. এই যে একটা স্লাইড আমি দেখিয়েছিলাম কত রকম চেঞ্জ করতে পারে দিকে, ডিপেন্ডিং অন কি ধরনের মলিকুল ওর উপর প্রয়োগ করা হয়েছিল। হ্যাঁ, ওর উপর যদি এমন একটা মলিকুল প্রয়োগ করা থাকে যেটা প্রোটিন বায়োসিনথেসিসকে আটকাচ্ছে, তা যদি হয় তখন ও কি করবে, ও চেঞ্জ করবে ওই জায়গাটায়, ও মডিফিকেশন করবে প্রোটিন বায়োসিনথেসিস যে মেশিনারি, সেখানে ও চেঞ্জ করবে। যদি এটা সেল ওয়ালে পড়ে তাহলে সেল ওয়ালকে ও আস্তে আস্তে চেঞ্জ করে দেবে, কিছু কিছু চেঞ্জ করবে, অ্যামিনো অ্যাসিড চেঞ্জ করে দেবে। হ্যাঁ, চেঞ্জ করে এমন করবে যে তোমার ড্রাগটা ইনঅ্যাক্টিভ হয়ে যাচ্ছে। তার মানে কি, ব্যাকটেরিয়ার একটা বুঝবার ক্ষমতা আছে কিন্তু, মানে এই যে মলিকুল আসছে ও কিন্তু নিজেকে অ্যাডাপ্ট করছে। ইট ইজ অ্যাডাপ্টেশন, অ্যাডাপ্টিং টু দ্য কন্ডিশনস দ্যাট আর বিং এক্সপোজড। ঠিক আছে, তুমি যে মলিকুল দিয়েছো সেই মলিকুল কোথায় কাজ করছে এটা দেখে ও অ্যাডাপ্ট করে নেবে, ওইখানটায় মিউটেশন করে নেবে, মিউটেশন করে ও চেঞ্জ করে নেবে। যেটা পেনিসিলিনের ক্ষেত্রে এইভাবেই হয়েছে। সেফালোস্পোরিন, ভ্যাঙ্কোমাইসিন সবাই এখন রেজিস্ট্যান্ট, সবারই ওই এমন মিউটেশন করেছে যে আর রিকগনাইজ করতে পারছে না। কোভিডেও এই সমস্যা হচ্ছে। যেটা হচ্ছে অ্যাডাপ্টেশন, মানে দিস উইল কন্টিনিউ, দিস ইজ ডারউইনিয়ান প্রিন্সিপল বেসিক্যালি।
তাহলে কোর্সটা কমপ্লিট করলে ব্যাকটেরিয়াটা মারা যায়, তাহলে এটা হতে পারে।
হ্যাঁ, তোমার যদি থেকে যায়, এটাই হচ্ছে প্রবলেম। কোর্স কেন কমপ্লিট করতে হবে? কারণ তুমি যদি কিছু রেখে দাও, তারাই তো চিনলো যে কোন মলিকুল ছিল, তারা তো বেঁচে আছে। এবার তারা যখন গ্রো করছে, দে অ্যাডাপ্ট টু দ্য কন্ডিশনস।
আচ্ছা,
কোর্সটা কমপ্লিট করা মানে ফ্লেমিং যেটা বলেছিল, ওভারডোজ হলেও ক্ষতি নেই,
আচ্ছা,
কিন্তু আন্ডারডোজ হলে প্রবলেম আছে। ঠিক আছে, আমার মনে হচ্ছে টাইম বোধহয় ওভারশুট করে গেছে।
হ্যাঁ, ঠিক আছে,
সবাই বোধহয় এখন লাঞ্চ ফাঞ্চ করবে মনে হচ্ছে।
কোনো আর কোনো কোয়েরিজ থাকলে আছে? থ্যাংক ইউ স্যার ফর সো নাইস ইন্টারেস্টিং টক।
Thank you. Thank you for listening.
Thank you.
We enjoyed this talk. Please over to Bidhan. Please go ahead.
না, আমার তো মনে হয় স্যারকে পুরো একদিন দেওয়া উচিত ছিল, স্যারের আরো যা ছিল স্লাইড আর কি।
এটাই মুশকিল। তুমি যদি টিচার হও না, শিক্ষকদের একটা টেন্ডেন্সি আছে বড্ড বেশি।
না স্যার, এবার জানার দরকার আছে স্যার, এগুলো তো
আসলে
আমরা অনেক মনে হয় আরেকটু হলে ভালো হয়।
রাইট, সেটা মনে হয়। আসলে একটা জিনিস বোঝাতে গেলে অনেক সময় লাগে, এই হচ্ছে ব্যাপার।
ঠিক আছে,
না বুঝিয়ে যাওয়া যায়, সেটা কোনো মানে হয় না।
সেটা মানে হয় না, মাথায় ঢুকিয়ে দেওয়ার একটা ব্যাপার থাকে, তো সেটা আমাদেরকে
এইবার নিজেরা পড়াশোনা করুন।
হ্যাঁ, ঠিক। Thank you, sir, for sparing your time.
Thank you very much.
Okay, thank you, sir. Our next session will be started just on 3 p.m. today. So participants are requested to join with us at 3 p.m. Thank you. This session is closed now for lunch breaking. Okay, thank you, sir.
Thank you.
Thank you. Thank you, Pralay. Bhalo theko.
Thank you, sir.